It's a great pleasure to introduce our speaker for the last lecture for today, Gordona Dukovic, who is an assistant professor in chemistry here at the University of Colorado at Boulder. Let us welcome our speaker.
Thank you, Ivan. So thank you all for staying late and for your patience. Can I have you come in a little closer? I don't hear very well, so when you start asking questions. So can you kind of gather up in the front? Thank you. So thank you for waiting. I had a 21-hour delay with my flight.
Wow.
And most of that was spent at gate C51 at Pittsburgh Airport, where I never want to go again. So as soon as we're done, I'm going to go sleep until our next session in the morning. So thank you. I want to start with a couple of really quick clicker questions because I would like to know a little bit more about you guys. So that I know a little bit about the audience, and then I'm going to have a couple of sort of real science-related clicker questions, so please get out your clickers. The first one is, I'd like to know a little bit about your background, because of, so I can maybe edit on the fly. So if you can start entering your answers, it won't take too long, just real quick. I'd like to see how many chemists we have. Like we're slowing down here. All right, we're mostly physicists. Good, you guys need to learn some chemistry. This will be fun. So we have quite a few physicists and then chemists, some engineers, and no others. Okay. Thank you. And I'm going to ask you real quick where you're from. So that's the next question. If you can start entering your answers really quickly. I heard that all the continents were represented, and of course we don't have enough options on the clicker side to group some together, but I want to see whether that's actually true and see how broadly it's distributed. Okay, so we have a few people from Africa and a few from North America and Australia, but we're mostly from Asia and Europe. So the next question then is going to be interesting. I'd like to get your opinion on who will win the next World Cup. Real quick, we've got Argentina, Brazil, Croatia, Italy, and Spain. Of course, we know that Germany is a contender as well, but again, we didn't have enough buttons on the clicker. I got 20. Any more opinions? There is the right answer to this question, by the way. There is the right answer, unlike the other one. Okay, let's see what you guys think. Ooh, we're pretty evenly divided here between these contenders. Of course, I need to close this. Of course, the correct answer is Croatia. So that tells you where I am from. So okay, so let's get started with some science now that we know each other a little bit better. So the title of my talk a few slides ago was really about semiconductor nanocrystals, photocatalysis, photochemistry, solar fuel production using these materials. And I've seen in your program that you've, unfortunately I was gone last week, but I've seen that you heard a lot about nanocrystals, also known as quantum dots. So I'm going to sort of dovetail with what you've learned from the other speakers, and maybe just start in the beginning by reviewing a little bit some of the properties of nanocrystals that are very important for photochemistry. And so, given that most people in the crowd are not chemists, I'm going to move this a little bit. I'm going to tell you what I mean by photochemistry, okay? So, as a definition, if you consider this little circle to be a semiconductor nanocrystal that absorbs light, and upon excitation, an electron and a hole are created. Can you do something about the lights? Yes. what you've heard about so far is photovoltaic uses of nanocrystals. So you've heard about ways of collecting these electrons in holes into a photovoltaic circuit. You've heard about multi-exciton generation. You've heard about how to make thin films that allow you to conduct these electrons in holes throughout the whole film and get them to electrodes. But what I want to talk about is photochemistry. So in addition to being really source of electricity, photoexcited electrons in holes are sort of like chemical reagents themselves, and I'll explain that in a minute, which means that an electron can really transfer to a molecule in solution. We'll call that an acceptor, that's why it's abbreviated as an A. And then that acceptor becomes what in chemistry we call reduced. It has one extra electron on it, that's what this minus sign means. And similarly, a hole, the positive charge, can transfer to an electron donor, D, to make now a molecule that's missing an electron. So that's really what we mean by photochemistry. So you can imagine these nanocrystals in solution, and there's some molecules floating around, and rather than collecting the electrons in holes as electricity, we actually use them to carry out chemical reactions. And just like for photovoltaics, for photochemistry, you also need to think about an energy level diagram for what actually needs to transpire in order for this to be successful. So what I've drawn here on the right is on the y-axis is energy, and so we have a semiconductor with a valence band and a conduction band, and it's photoexcited. And so basically the energy of this photon has now been transferred into what we call a reduction potential of that electron. It's transferred into now this electron has excess energy, and it could relax in several ways. It could relax by recombining with the hole. That's photoluminescence or fluorescence. It could non-radially relax. But again, it could also transfer to that acceptor molecule to reduce it. And in order for this to be favorable, it really needs to be energetically downhill. And so there needs to be an energy level in the molecule somewhere below the conduction band of the semiconductor where the molecule can accept an electron. So this process needs to be downhill in energy. Similarly, for the hole to transfer to another molecule, in other words, to pluck an electron out of a molecule here and put it into semiconductor valence band, there needs to be an energy level with 2 electrons here, or at least 1 electron there. And so you can sort of see that the levels, the sort of molecular orbitals that will accept electrons or donate electrons sort of need to be sandwiched inside the band gap of your semiconductor in order for photochemistry to really be favorable to occur. And so that places some real sort of stringent requirements on the band gap of the semiconductor. They're more stringent than photovoltaics in many ways, because not only does it matter that you have a band gap that will absorb the kind of light that you have, but it also needs to, absolute band positions need to be fixed in an absolute sense with respect to sort of the vacuum level compared to the molecular orbital levels. And so that's sort of what I mean by general photochemistry of nanocrystals. And today, so there are 2 questions. I'll address one today, one tomorrow. Today we'll just talk about nanocrystal photochemistry in general. How do we think about this process? What does it depend upon? Is it competitive with other processes? And then tomorrow we'll actually talk about how to use that kind of photochemistry to do useful chemical reactions like solar hydrogen production. And so photochemistry is really not even a field yet in nanocrystals. When the nanocrystals were first discovered in the 80s, there was quite a bit of interest in doing photochemistry with nanocrystals, but back then the samples weren't very good, and the main problem was that there was a lot of photooxidation, so these holes would actually sort of dissolve the nanocrystals themselves. And so nanocrystal photochemistry really sort of died off very, very quickly. And now, very recently, it's been coming back again because now we have much better control of synthesis. We have much better understanding of photophysics, of all the other processes that occur in nanocrystals. And so this is what I would argue. There are not many people working in photochemistry, but I would argue that now is sort of perfect time to really take photochemistry and make it into photochemistry and nanocrystals into really, quantitative science where we really understand what's going on. So this is a pretty sort of information-packed slide that has the basic concepts. I want to just stop here and see how we're doing and whether there are any questions. So I have a question for Ivan. How much time do I have? When do I need to stop talking?
You still have about 35 minutes.
Okay. I can keep going for a long time, so I need to know when to stop. Good, yeah. So any questions? Did I see a hand go up? You can see me better than I can see you, so just yell out. Okay. So just sort of as an outline again, we have sort of 5 points that we'll address, not all of them now. So just the first 3. Very quickly, we'll review what you've already learned about nanocrystals. You've had 4 speakers so far on the subject. And then we'll talk about sort of how do we measure rates of photochemical reactions, what does it really mean for photochemistry to be occurring, what do the experiments look like. And then we'll talk a little bit about the theoretical framework for how do we think about controlling photochemistry, what do we need to do to nanocrystals to improve rates of photochemical reactions. And then, as I said, tomorrow we'll talk about sort of more practical uses of this. So let's just review a few things. And I'm not going to sort of click or question you on this just to save time, but you've already seen this. Anybody not seen this? Or how many people have seen something like this? Good. Good. The speakers, what I thought they were going to talk about, they did talk about. Good. So what we do know already is that one of the things that's really amazing about nanocrystals is that we can really control their spectra very, very, very precisely. And so this is the famous example of the size of cadmium selenide nanocrystals, controlling their light absorption spectra and the emission color. And we can do a lot of things other than just looking at size. Compositions, nanocrystals can be made up of many different materials, all of which have their own band gap and therefore their own nanocrystal spectra due to quantum size effect. So it's really, really important to remember that we can really tune the band position. So when I talked about how important it is for the valence and conduction band to be properly placed in order for photochemistry to really occur, with nanocrystals we can actually tune that and sort of find the best energy band positions that we want. Okay, so the other property I want to point out, this is just a little bit more about the spectra. What you probably, does this look familiar? Raise your hand if it does. Okay, not a lot of hands went up. So this is the absorption spectrum of cadmium selenide nanocrystals. So you probably saw many spectra already, but they have energies increasing in this direction. And so you see several peaks in the spectrum, whereas in a semiconductor that's bulk, you would just see one big sort of quadratic band, direct band gap kind of behavior. So what these peaks are due to are all these quantized transitions that occur near the band gap because, again, of the quantum size effect. Raise your hand if you remember what quantum size effect is. I did have to go. I had to save some time, so I did not review all that again. But we do have these discrete energy levels that are due to the quantum size effect, and so this is not, a mixture of different sizes that you're looking at in the spectrum. What you're looking at is the peaks due to various transitions within one particular size of the nanocrystal. So the spectra are quite rich, actually. Okay, the other point I want to make is You've probably heard a little bit about the synthesis. So nanocrystals are made, this is actually a video, but we don't have time to play it. They're made in a kind of what maybe a physicist would consider an unsophisticated way, but what a chemist would consider a well-controlled way, because we can tune a lot of the parameters in solution. But they are made in solution at pretty high temperatures, and we start with atomic precursors, so some molecule that contains the cadmium atom, and some molecule that contains the selenium atom, and some other molecules that end up sort of sitting on the surface. And so this is all in solution at a high temperature, and because it's such a high temperature, all these molecules actually decompose, and because of the specific chemicals that are used, what ends up happening is creation of the cadmium-selenium bonds. And the other thing that ends up happening is that there are organic molecules, so molecules that have hydrophobic or oil-soluble, very long chains that are kind of sticking out in solution, making the nanocrystals soluble in organic solvents. It's also well understood by now that we don't only have to have organic soluble nanocrystals. We can then take these big molecules and replace them with other molecules that are maybe making the nanocrystals water soluble, or maybe the molecules are shorter, or maybe they help you make better films. So do you remember any examples of this kind of ligand exchange process? Did anybody talk about it last week?
Yeah.
I know somebody did. Who talked about it?
I don't remember who it was, but...
Very young, middle-aged, or old gentlemen? No, okay.
Or, I think middle-aged.
Middle? Okay, Matt Beard. Yeah.
Yeah.
So, don't tell them I put them in these age categories. So, there's a lot we can do to the surface, and you've seen already that the surface actually plays a big role in some of the properties. And so it's really wonderful what we can do with nanocrystals, controlling their optical spectra, controlling their surfaces, controlling, as you'll see, photochemistry as well. So that's why they're so exciting to nanoscientists and to chemists, is that we can really tune a lot of the properties. So that's really all I wanted to sort of review, and just to summarize the properties that are particularly important to photochemistry. Nanocrystals are actually very strong light absorbers, so they're usually made out of direct semiconductors, which means that they absorb light strongly, just like gallium arsenide does. And so if you're a chemist, you're familiar with the term molar absorptivity in the units per molar per centimeter. If you're not a chemist, don't worry about it. But this is a pretty large number, million to 10 million per molar per centimeter. So they're much stronger absorbers than molecules, for example. Even possibly per atom. Depends on what molecules you're comparing. So they can absorb a lot of sunlight. As we mentioned, they have tunable absorption spectra, so they can be adjusted as needed for a particular purpose, tunable surface chemistry, and also high surface areas, which is what's important because of all these photochemical reactions that we're interested in are occurring at the surface. So having a high surface area to volume ratio is very useful for getting very efficient photochemical reactions. There are some potential challenges. The photooxidation of chalcogenides, this is sort of still debated whether this is a solvable problem or not. I think it's solvable. It's also, because we have these high surface area, possibly we have higher rates of reactions that we want, but we might also have higher rates of reactions that we do not want to have happen, sort of back reactions, and so that's another thing that may occur. But really, at this point, we don't know. We really don't know how the photochemistry field is going to play out. We really don't know what all we'll be able to do. So we'll just have to wait and see. I guess that's what we'd call being on the frontier. So we'll see how it goes. So that's it for the review. Now I want to tell you a little bit about how we actually sort of measured the rates of photochemical reactions and how we measured their competitiveness with other relaxation pathways. Any questions about what I've said so far? Okay, so try to keep paying attention because there will be a quicker question coming up. Okay, so how do we actually measure the rates of photochemical reactions? So here's a and it's sort of on purpose a very complicated diagram, showing you all the possible, or some, or many of the possible energy, relaxation pathways for a photoexcited state in a semiconductor or in a semiconductor nanocrystal. So let me sort of walk you through it a little bit. The energy again is on the y-axis. Valence band is here, conduction band is here. I'm not showing the quantized levels just for the sake of simplicity. So once there's a photoexcited electron in the hole, processes you know about photoluminescence occur in about 10 nanosecond or longer time scales. There are also sort of states that can be on surfaces called trap states, which you've probably heard about already. So like both electrons and holes can localize in these trap states that can be quite long-lived, and even those trap states can actually result in emission of different colored light, so that appears in the emission spectra. So those are kind of the, or of course both of the radiated pathways could also have similar non-radiated pathways associated with them, and that's all when you only have one electron, one in hole. If you put in multiple electrons in holes, you have even more possible pathways. But that's sort of what most sort of people study, is the photophysics. You know, how fast are the radiated pathways versus non-radiated pathways, for example. Quantum dots are used a lot in sort of lighting applications and LEDs and things like that, where you really want to maximize competitiveness of the radiated pathways here. But now, when you add molecules, when you add on top of all this an electron acceptor, shown here on the right with its HOMO and LUMO, anybody, or how many people know what I mean by HOMO and LUMO? If you've heard about organic PVs, you know. Okay, great. So highest occupied molecular orbital, lowest unoccupied molecular orbital. There are 2 electrons in here. This orbital has no electrons. And so this is where an electron might be accepted into this orbital. So you have this process here. There could be a back electron transferred and from this orbital to recombine with this hole. The hole could transfer to the orbital here that has 2 electrons in it. In other words, there are a lot of things that could happen, and they all may be happening, and basically the fastest process wins. So 10% of the excited states may decay by this pathway, in which case you would have a sort of 10% yield of photochemistry and 90% yield of what I would call photophysics, all the processes that are happening on the inside. So it really is a matter of rates. How quickly is each decay process occurring? And that's why we're sort of obsessed with kinetics and measuring the excited state dynamics and how quickly the excited states decay. Any questions on this very complicated graph? They're going to get simpler from here. Okay. So how do we actually measure these processes? So I've now simplified the diagram quite a bit and decided to just look at electron transfer, sort of remove a lot of the other things from the picture, so that's what's sort of shown in here. But the similar principles apply to all the other, to the whole transfer side of the equation. And so I put in a particular electron acceptor here, hydrogenase, which I'll talk about tomorrow. And now we're looking at cadmium sulfide nanocrystals, and I am showing you the quantized energy levels near the band gap. And so, you know, if you don't have the acceptor, cadmium sulfide gets excited, and then there's some rate of excited state decay that's some combination of radiative and non-radiative processes. And so we can just summarize all of those as K cadmium sulfide, just things that are happening in the nanocrystal itself, all the decay processes. And then we have this, once we have the acceptor present, we have this new process, the electron transfer. So now, the overall excited, once you have the acceptor there, the excited state is going to decay faster, because not only do you have this rate, but on top of that you have the electron transfer rate. So basically the rate of the decay of the excited states for the complex meaning the cadmium sulfide plus hydrogenase, is the rate of the excited state decay in the nanocrystal itself plus the rate of the electron transfer. And rates in spectroscopy, when we do time result spectroscopy, when we really measure our lifetimes, which is just inverse of the rate. And so the way this sort of manifests itself in our experiments is that if you have some electron population plot, so this is 100% photoexcited and this is 50% electrons left and so on, if you're looking at the electron population as a function of time after excitation, without the acceptor you'll have some kind of a decay that has some time constant here. I've drawn single exponentials just for simplicity, and once we've added the acceptor, the decay speeds up for the reasons I just explained, that there is now an additional pathway removing those electrons from the excited state. And then the quantum efficiency of electron transfer is the rate of the electron transfer over the rates of all the other processes. So I'll tell you in a moment how we actually do this kind of spectroscopy, and you've heard about it from Matt Beard as well. But if you were just to, by some method, measure electron population as a function of time after excitation, this is what you'd find. With electron transfer, you'd find shortening of the lifetime, and of course, the more efficient the electron transfer, the shorter the lifetime gets, and therefore the higher the quantum efficiency of electron transfer. So these equations are kind of sort of textbook examples for chemists, but may be new to other people. So it doesn't, I don't want to get too obsessed with equations. I just want to sort of point out how this plays out, is that you just sort of see a lot shortening, and from comparing the decays with it without your acceptor, you can get all the three quantities. The rate of decay of the nanocrystals themselves, the rate of decay of the complex, and the difference of the two is just the electron transfer. So I think the next thing is a clicker question. So get ready, and you can take a little bit of time to think about this. But I've shown here 4 different experiments, hypothetical experiments, in which in the blue is the same in all of them. That's the electron population decay as a function of time of just the nanocrystals. And then in this sort of reddish, purplish color is the decay of the excited state with the electron acceptor present. And so I'd like you to tell me what the quantum efficiencies are. So I've sort of listed some possibilities: 20%, 50, 10 and 15, 90, 50, 25, and 5, 20, 50, 90%. So it might take a little bit of discussion or thought, but I'm going to start this, and and you can start. Got some answers. Feel free to talk amongst yourselves. Yeah, do you have a clicker?
I don't.
Bad student, yeah, bad.
I'll give you the answer.
You will? You're going to want to guess? Okay, I have 29, 31, I think, 32. I think that's about the number of people in the room, so I'm going to stop it here. Let's see how it... Okay. Oh, yeah.
B will be my answer.
Yes. Good. Very good. Yeah, that's correct. Okay. So good. This was sort of making sure that you're awake and the language that I'm using is making sense. So, so we don't have to worry about the equations. We can sort of qualitatively think about this. Okay. So there it is. Next slide. Okay, so how do we actually do these experiments? Again, one method is that I'm not talking about here is photoluminescence, but I'm going to talk about transient absorption, but the principles are similar. We're measuring how many talks have you heard about transient absorption spectroscopy? Any guesses? Now, yell out some numbers. One? You've heard one talk about transient absorption? Sorry? More? 2, 3? Okay. I almost had a clicker question asking you how many talks you've heard so far, but I didn't think it would be good.
113.
Yeah, so I know it's all blending together. So the experiment basically allows us to control this, to excite nanocrystals and then wait for a very set period of time and then excite them again. So this is a very simple schematic here. You have a sample. We use 100 femtosecond pulse to photoexcite nanocrystals, create an excited state population, and then after some amount of time, we send a second pulse, which is white light, and it's just taking an absorption spectrum, just like you would with a regular UV vis. If you take a regular UV vis, you're taking the absorption of the ground state, but here you're sort of taking it, I don't want to complicate too much, but basically you're getting the excited state spectrum, absorption spectrum of the excited state, so you're basically taking a UV vis, meaning that you're collecting the transmitted white light. And so what we end up having is this is real data from my experiment in my lab. This is actually a really large file. It has many points in it. But what we have on one axis is the spectrum, and what we have on the other axis is the time delay between the first pulse and the second pulse. And then we have some features that correspond to certain transitions in nanocrystals. And so this feature here at 470 nanometers is actually exactly, is exactly this transition right here. Okay, so it's telling us about the population of the excited electrons. Its intensity is directly proportional to the population of the excited electrons. Okay. Oh, it's slow because the file is so huge. Yeah. Sorry. Big data. So actually that's one of the issues we have in our lab, is that our laser setup is so powerful that we get so much data, and then we're sort of careful what you ask for, because we're finding out things that people didn't really understand before, just because we're able to collect a lot of different kinds of spectra. But anyway, this is a photograph of what the laser setup looks like, and I don't want to bore you with it, but it's a little bit complicated. But so this transition here basically tells you the population of the excited state electrons, and you can see that as the time goes by, the time between the pump and the probe here, the time goes by, that transition reduces in intensity as the electrons decay from the excited state, and that this is real data again, showing that same electron acceptor hydrogenase. So in the red here, it's upside down due to a strange convention, don't worry about it, but basically -1 means full population of excited electrons, and then 0 means no more excited electrons. And so over time, the electron population decreases like this. It's actually multi-exponential, not a single exponential decay, but that's just a technicality. And then when there is the electron acceptor, we see that the population decreases faster. And it's basically, if you were to just integrate under these curves, which is actually the integral under curve is proportional to the population, we see that basically you have half as much population of the excited state when there is an electron acceptor than when there isn't, which tells us that the quantum efficiency of the electron transfer in this is about 50%. Okay, so it's sort of like the lifetime thing that I was talking about, but just a little bit more complicated because of the multi-exponential nature, but it's the same thing. It was that example B, or the second decay that you most of you correctly answered. So this is what real life looks like. So we really can measure both the rate and the efficiency of electron transfer. And so when you get something like 50%, that means that photochemistry is reasonably competitive with photophysics. Half the time your excited state will decay by photochemistry, but another half the time it will decay by photophysical pathways. So it's reasonable, but of course we want it to be 100% efficient. If we are interested in the photochemical product, we want to try to push that limit. So with that in mind, I'll tell you one thing you can do to try to increase, sort of push it from 50 to 100. This sort of textbook definition of quantum efficiency, again, is the rate of the electron transfer over all the other rates. And so if you just decrease the rate of the excited state decay in the nanocrystals themselves, then the electron transfer can be more competitive, because now the excited states in the nanocrystal itself are longer lived. And so there's more time for photochemistry to occur. And one of the ways to do that is to make what we call a type 2 heterostructure, and you've seen this in many instances of photovoltaics, many energy level diagrams like this, but we can actually make nanocrystals that are sort of half zinc selenide and half cadmium sulfide, and this is how they're, these are the valence bands and these are the conduction bands, and so electrons go into cadmium sulfide and holes go into zinc selenide, and now the recombination is slowed down by quite a bit, because now they're in two separate parts of the nanocrystal. The electron is in one part. This is an image in our synthesis. Our synthesis has improved quite a bit, but for a long time we were sort of making nano boots. There were little zinc selenide legs or feet coming off of the cadmium sulfide rods, but we've got a little better control at this point. So, longer lived excited states, we're testing right now whether that will actually give us, closer to 100% electron transfer to this hydrogenase enzyme. Yes, we have a question.
For the decay rate,
Yeah.
when you decrease the decay rate, the electron transport will be increased, yes?
No. So in the simplest terms, because what matters for the electron transfer is where the cadmium sulfide conduction band is, and that hasn't really changed because the electron is still coming out of cadmium sulfide. So what we're keeping into zero closure, we're keeping the electron transfer part constant, because the electron will still be coming out of cadmium sulfide. But what we're changing is this value here. This value here will be decreasing. So the lifetime of the heterostructure, or the lifetime of the excited state, the lifetime of this electron, if you will.
But these two values are related together, because these are the rate of the excitons. That means the Kd is the rate of the exciton which will decay, and the electron transport is the rate of the exciton. Yes, and we have for example, the generation of the exciton. That means these two rates should be related together, because we have an exciton only if you consider as an equilibrium.
Okay, so are you speaking sort of from a more organic perspective? Yes. Okay. So in organics, the excitons are very tightly bound, very highly correlated, and so it's sort of impossible to not perturb other things when you change the exciton, when you separate the electron and the hole. In nanocrystals, the electron and the hole could almost be considered to be independent carriers. So exciton binding energies are not very large. So you can sort of just think of, this electron is now sitting in the same place as it was sitting in the cadmium sulfide nanorods themselves. And it doesn't really, the fact that there's a hole here does not really change the energy of this electron here. And so what we've changed is the rate with which this electron recombines with this hole in the nanocrystal itself, but we didn't change the rate at which it's transferred into another species in solution. So, by independently just changing this, my computer's trying to back up because it usually backs up at this time of the day, sorry. So we're really only changing what's going on inside the nanocrystal, the recombination inside the nanocrystal, but not the rate at which this electron goes to another species that's on the surface. So does this answer your question, or do you want to talk about it?
Discuss later.
Yeah, let's discuss it. Does anybody else, is this confusing to anybody else? Should I spend more time on it? Just feel free. We got, 3 more hours. And I can just stop whenever you tell me to stop, so whenever you start throwing objects in. So, So this is just an illustration of, again, what kind of level of control we have with nanocrystals. We can now make more complicated structures that perhaps will be better suited for photochemistry. Okay, so finally, let me just talk about the theoretical framework for nanocrystal photochemistry. Now I'm going to have to ask again how much time I have.
25 minutes, 20.
Oh, really? Awesome. Okay. Excellent. Okay, so we've talked about how to change the photophysical pathways in the nanocrystal without actually changing the rate of electron transfer. Now we're going to talk about how to change the rate of the electron transfer. So how many people are familiar with Marcus' theory of electron transfer?
They all should, it's all heard about it.
Oh, you have from who?
Sean actually told me about it.
Sean? Okay, so this was a couple of weeks ago?
Yes.
So I actually heard Rudy Marcus talk about it himself last Monday. So I got the, it's coming from the horse's mouth. Rudy Marcus is very famous for this Marcus theory of electron transfer. He won the Nobel Prize for it. And the wonderful thing about it is that it's a fairly simple, compared to other theories, it's pretty simple and it can be quite useful, and we actually don't really know whether Marcus theory really applies to nanocrystals yet or how it plays out in nanocrystals, because again we're just beginning to apply Marcus theory to nanocrystals. But I'm gonna have a clicker question, so pay attention. I'm just gonna tell you, try to give you sort of a very abbreviated version of Marcus theory. Let's see how I do. Okay, so maybe this is looking familiar from Sean's talk, but Marcus theory is sort of the science of parabolas. These are not, just imagine that these are parabolas, okay? I drew them with freehand, but they're parabolas in Marcus theory. And what I'm showing on this diagram here, I have a free energy on the y-axis, and I have something called a reaction coordinate on the x-axis. Reaction coordinate's kind of a strange sounding term. It could mean things like arrangement of solvent atoms around a molecule. It can mean many different things, but it's kind of, we can just sort of think about it as I'll explain in a moment, it might make more sense, but we can just sort of think about it as some kind of geometric representation of a donor, electron donor, and an electron acceptor. So, free energy, chemists, we like Gibbs free energy. I know physicists prefer Helmholtz, but we're gonna, do you guys prefer Helmholtz?
Yeah.
Yeah. We're gonna have to stick with Gibbs for this one. So this parabola here on the left is showing how the free energy of the donor-acceptor pair, so let's say our cadmium sulfide nanocrystal with hydrogenase acceptor on it. So nanocrystal, maybe with an electron acceptor on it, just neutral without electron transfer happening, just sitting together next to each other. And so this is, as I said, a parabola, and there's a minimum down here, and this is sort of the reaction coordinate, maybe the arrangement of all the atoms and the atoms in the nanocrystal and the molecule on the surface that gives it the minimum free energy. So that's sort of, you know, the arrangement that that complex is going to take most of the time. And then we have on the other parabola corresponds to the situation when the electron transfer has occurred. So now there's the electron is on the acceptor, that's what this little minus sign means, and there's now electron missing from the donor. So the hole is on the donor, and that's what the plus means. And that has its own parabola, and you know it's arranged with some, depending on the details, it's related to the other parabola in some way. And do we need to sort of pick out three quantities that come from this arrangement of two parabolas? One is the most obvious one, the free energy difference between the free energy of the donor-acceptor pair and the free energy of the charge-separated pair. And so, obviously in this case, this is an exoergic reaction, where the the separate electron electron being on the acceptor and the hole being on the donor is lower in energy. Okay, is lower in free energy, and so this is delta G for this electron transfer is negative. So that's a spontaneous electron transfer. The other thing we need to think about is electron transfer doesn't just sort of occur out of nowhere. All these sort of atoms and things need to move a little bit. The system needs to sort of actually allow this electron transfer to occur. And so, in the very simplest terms of thinking about it, the way this happens is there's a point at which this process can go through, and that's the point at which this parabola and that parabola intersect. So they're at the same energy. So then it's the same energy for the for the electron to be on either parabola, and so this is what you call the transition state for the reaction, and the height of this difference between the bottom of the higher parabola and this intersection is the activation energy, in the simplest terms. So that's the very important quantity in chemistry, because the higher the activation energy, the slower a chemical reaction is. No matter, even if it's a very energetically favorable reaction downhill in free energy, if there's a very high barrier, the reaction is going to be slow. And so you've probably seen this formulation before. The rates of chemical reactions usually go exponentially with minus activation energy over kT. And then the third quantity I want to point out is this sort of thing called reorganization energy, lambda. And it can be a little bit puzzling for people to understand when they first start learning about Marcus theory. But it's basically the difference in energy. It's the energy required to be in this nuclear configuration, so to have the nuclear configuration of the charge separated state, but not be charge separated. In other words, to be in the non-charge separated state, but have the geometry of the charge separated state. Did that make any sense? Okay, good. If you Wikipedia, actually I know the guy who wrote the first Wikipedia article on Marcus theory back when we were in grad school in early 2000s. So he talks about reorganization energy. So, it's basically telling you something about how much of a perturbation is the whole system to actually separate the charge. Okay. So now I'm going to have a clicker question. I got rid of some of the axes and definitions just to make things easier to see. I have three sort of arrangements, all of these are exoergic reactions. The free energy is delta G is negative. So I'm going to ask you which one is the fastest, A, B, or C. And I'm going to start the clicker. So don't answer D or E. I like the clickers. This is fun. Uh-oh, I got 26 answers and I got 32 before. Need a few more. Or did 4 people walk out and protest? Okay, well, I want you, maybe, why don't we discuss this and talk, let's see what the answers are and maybe talk about the rationale, depending on how the answers look. Oh, they're pretty evenly divided. We have some preference for B, but it's not super strong. So let's argue a little bit. I can be the jury. You know this is for the jury, right? If you've seen in the American TV shows, Law and Order and so on. So who wants to argue for A? What makes that the fastest reaction?
checkpoints for me, so.
I'm sure there's a valid reason, so let's, or there's a reason anyway, let's hear what it is. Anybody? Anybody want to argue for C? C is a very exergic reaction. Very large driving force. That's another name for delta G, driving force. Who wants to argue for C? I can't blame you for picking C. Go, yeah.
I don't believe in absorption reaching.
Okay. We can talk about that. Okay. So you really don't?
No, I.
Oh, okay. Oh, you're just being objection. Okay. Anybody want to argue for B? All right. We have a. What's your name?
Masood.
Masood. Go ahead.
In the case of B, the activation energy is very close to zero.
Yes.
So by having the minimum activation energy, it means that we will have the highest kinetic, according to the previous formula which you showed on the previous slide. Because the barrier is the activation energy. Since we don't have the barrier, or the barrier is too small, so the reaction goes forward fast.
Okay. Any objections? That was a well-reasoned argument, well presented. Any objections? I'm the jury. I like sitting here. Any objections to this argument? All right. So that is correct, unless you don't believe in the invergent region. So what I wanted to really get at here is, that's exactly, he said it, Masood said it just the way I was going to say, but what I wanted to get at here is, there's all these quantities I just discussed, and I just wanted to again re-emphasize that the main thing is the activation energy, the height of the barrier, and really the way this is the science of parabolas, and I can show you an exercise in which you can derive the big equation I'm going to show you in a minute. But the rest of sort of dependence of activation energy on the reorganization energy and delta G, it all just comes out from geometry, from the parabolas. And so here we have the activation energy from here to here. Here again it's almost zero. And then here it's from here to here. That's actually a very high activation energy. So even though the driving force is large, the activation energy is also large. And so the sort of big equation that it's actually not the biggest equation because there are more sophisticated versions of this equation and quantum mechanical versions of this equation. But the equation sort of describes the rate of electron transfer, has of course 2 pi over h bar, and then it has actually the electronic coupling between the donor and the acceptor. It has some constants, of course lambda is not a constant, neither is the temperature, but mainly has this exponential dependence on the minus lambda plus delta G squared. So remember, delta G is negative. And so you can see from here that when lambda equals delta G, that's actually when you have the highest rate. And that also happens to be because, again, of the science of parabolas, this point here. And so this sort of tells you about how the rate depends on, so it's not just the driving force that matters, it's the driving force versus reorganization energy. And the driving force is something that we can change because remember, in nanocrystals we can certainly move the energy levels up and down of our conduction band, and I'll show that in a moment. And the other thing that's very important is this donor-acceptor electronic coupling. So that's again sort of somewhat vague notion, but it basically, you can think of it as the overlap of the wave functions of the donor and the acceptor. So this is a little bit more of a quantitative expression, but I think if you just remember that you want to minimize the activation energy, that's probably the most important thing. Any questions here? Yes?
Could you please explain that inverted region?
Yes.
If delta E of A and C is same,
A and C, okay.
if delta E of A and C is same.
If delta G,
Yeah, delta G. Yeah.
if the curves were otherwise the same and you had the same delta G, I don't think you would end up like this. So it's a little, I have to a little bit think about just again the science of parabolas, but the way they sort of move with respect to each other, you would have to have a situation maybe to get over here, you'd have to sort of have a situation where the bonds are actually compressed when you have the charge separation, so that would be sort of an unusual situation. Does that help? Okay. Any other questions? Yes.
Is there any relation between lambda, the reorganization energy, and EA, activation energy? A direct relation.
Yes, so the three of them are related, activation energy, lambda, and delta G. So together they're... Do you guys take homework? Do you have homework? I can give you a problem on this, that'll make it over. Yeah? I could, okay, so, you know, I'll probably sleep between now and the next step, but I'll try to dig up a problem I can give you. Because once you work it out on your own, it makes a lot more sense, because it really is just parabola. Other questions? Okay, so in the next couple of minutes, I'm about to wrap up. I just want to show you how this sort of manifests itself in nanocrystals. So we don't really know whether this is really a good theory for describing describing electron transfer from nanocrystals. It looks like it is from sort of what people have been seeing in their data, but again, we're still learning. See, the papers are pretty recent. Here's one from 2011, where this group has an electron transfer to a molecule called methylviologen, which has an acceptor lying right here in energy. Again, the y-axis is energy. And then they have nanocrystals of various sizes. And so when you change the sizes of nanocrystals, you're changing the conduction band positions, and so therefore changing the driving force. So the smaller the nanocrystal, the bigger the band gap, the higher the conduction band, the larger the delta G. These should be not quite as separated because most of quantum confinement actually goes to the electron, but that's okay. So it's really hard to tell from this plot where that's a log plot of the rate of electron transfer versus the free energy based on this difference here. It's really hard to tell whether it's quadratic, which it should be, right? It should be quadratic, or why they put a line through it. It's a little hard to tell from this data, but maybe there's definitely sort of a trend that you'd expect that as you increase the driving force, as long as you're in this, I forgot to mention that, as long as you're in what's called normal regime, the rate of electron transfer is increasing. So this is sort of called the Marcus normal region, where you have, you know, the more you decrease the delta G, the more you're going to be sort of, your parabola is going to be lowering and lowering until it gets to this point. But then as you continue to lower your parabola, again, you kind of cross to this side, and that's called the Marcus inverted region, where as you lower the parabola and increase the driving force, you actually also increase the activation energy and decrease. And real proof, and that has not been shown in nanocrystals, the proof of whether Marcus theory works for your system is when you find the inverted region. It's not that hard to find the normal region, it's finding the inverted region that can be a problem, especially when you have nanocrystals with a lot of different energy levels, but that's a little bit of an advanced discussion. So what is coming out though is that it's thought that reorganization energies are pretty small for nanocrystals, because really taking out one electron does not really change the nuclear coordinates of the nanocrystals very much, because it's a big chunk of thousands of atoms. Not like a molecule that has only a few atoms and you move one electron and all the bonds have to rearrange a little bit. So, the jury's out, we don't really know. So that's the sort of the driving force effect. And then the other effect I just want to show you is we can't change the electronic acceptor, the electronic coupling between the donor and acceptor. So cadmium sulfide in this case is the donor, photoexcited cadmium sulfide, selenide, sorry. This is a paper again from 2011. and the acceptor is TiO2, so our friend from dye-sensitized solar cells. And this drawing is a little silly because I don't know what these curly little things are on the surface, but this is supposedly the case of nanocrystals being directly adsorbed onto TiO2, and so the coupling, sort of the electron wave function, extends into the TiO2. It sort of bleeds in, you know, at the tail of the wave function. Whereas in this case, there's a molecule. This is, for the chemist, mercaptopropionic acid or mercaptopropionate. So the carboxylic acid sticks to the TiO2, and thiol N sticks to the nanocrystals. And so now there's sort of a spacer, and so the electron wave function from the nanocrystal doesn't quite bleed into TiO2 as much. So there's less coupling between the donor and the acceptor, and they do find that this situation leads to 3 times faster electron transfer than this situation, and then several people are working on making this even more quantitative. So, this is my last slide, and it's got a lot of words on it, so I just want to sort of conclude and review what we talked about today, and have our conclusions listed. We reviewed some properties of nanocrystals, and we talked about how we can measure the rates of photochemical and photophysical decay pathways by time result spectroscopy. And then we talked a little bit about how Marcus theory may be a theoretical framework for guiding us to sort of, if we want to increase the rates of electron transfer, we need bigger driving forces unless we're in the inverted region. You know, how do we think about how to increase the rates of electron transfer through this framework of Marcus theory? And I've also shown you a couple examples of how you can tune the driving force and the electronic coupling with nanocrystals to again control the rate of the electron transfer. So I believe, yeah, these are just exercises. So this is my last slide for today, and I can take more questions now, and we can, or I'll take applause. But we can have more questions, or we can have some sort of more informal discussion over here, or
Any direct questions for Gordona?
No more questions.
Coster,
okay, you guys are ready for dinner, aren't you? I'm with you. Okay, well, thank you.